In the next segment, I just want to talk about the first two sections of chapter 19. I'm also going to do a segment about the third section of chapter 19. I won't lecture about section 4, that'll be up to you. And then sections 5 and 6 and later sections we will save for a later date. So in this segment, sections 1 and 2, in another segment, section 3, and that'll be it for now. All right, so it's in chapter 19 that we start our work with symbols and electric circuits. So we start drawing electric circuits abstractly using symbols to represent the things that we've talked about. A line is going to be our representation of a wire. So this is a good conductor of negligible resistance. We can pass current through this all day long. Whatever the resistance is, it's super low, and so the energy that we dissipate by pushing current through that small resistance is also negligible. So we're pretending that this wire is a conductive connection with essentially zero resistance. Okay. If we want to talk about a resistance, we'll use this kind of jaggedy representation. That's our resistor symbol. If we want to talk about a source of electrical power, I'm going to draw it that way. It's a this is a cell. Technically, if we want to be very technical, to draw a battery, we might use this symbol, but a lot of the time you'll just see me use this one to mean battery. So this is a source of potential difference. Think of this like an electrical ski lift, pushing charge uphill in the potential environment that they live in, so that they are at a high point of potential, and then they fall back down. Now they're at the bottom of the hill, and the ski lift picks them back up again, and the battery just continues to do this, continues to ski lift charge up the electric potential hill so that they can ski down. The bigger the hill, the greater the potential difference. Okay. So, we've talked about Ohm's law. And so we can say something in the language of Ohm's law and draw it in the symbolism of circuits. That there is some potential difference, some resistance, and that some current flows. Our convention is that we're talking about positive charge carriers flowing. Positive charge carriers would flow away from the positive electrical terminal and towards the negative electrical terminal. A positive charge flows downhill naturally, and then the battery picks it back up again, puts it towards the higher electrical potential so that it falls around the circuit. We know that it's not positive charge carriers that actually move. We know now that it's electrons, the negative charge carriers, doing the current. But the choice to track positive charge carriers was made in the late 17, early 1800s by Benjamin Franklin. He's okay, electricity, positive charge carriers, that's the direction of current. And he might as well have flipped a coin for all for all he knew at the time. And for all I know, he did flip a coin. The point is, he ended up picking the wrong charge carrier, which means what we call conventional current isn't actually the direction of current. When we talk about positive charge carriers going this way, what's actually happening is electrons going the other way. For all our purposes, they are equivalent, and we can just talk about positive charge carriers going one way, like electrons going the other way. It's the same. So I'll draw the current that Ohm's law predicts this way from the positive terminal around the negative one, and we'll call that I. And this is a sort of a pictorial statement of Ohm's law. Okay. Now, there's a couple things we got to say about this. Thing number one, charge is flowing. We're talking about current. We want to keep this charge flow streamlined. If this is all one pipe, there's only one place for the charge to flow, and there's nowhere for it to back up, bunch up, get collected. There's nowhere for it to pool. On this side, as we move charge into the resistor, we have to move an equal amount out of the resistor. Otherwise, it's going to get tangled up in here, and we have to continue moving it around through the battery so that we have a nice, consistent current all the way through the loop. Okay, the other thing we've got to say, the battery does work to push charges through its electrical potential difference. Those charges have energy now that they didn't before. And on their way through the resistor, now we have to push them through the resistor. And you can almost sort of see that it's the resistor that tells us how high the hill needs to be for a given current. Or in other words, yeah, the greater the resistance, the greater the potential difference has to be in order to obtain a particular current. Yeah. Think of it like well, the greater the resistance, the harder it is to go through on your own if you're a charge, the greater the height you must have started from, so that by the time you get to that resistor, you have more kinetic energy to kind of ram through that resistance. But once you're done, I don't want to have energy left over. Now I'm careening around and I'm going to smack into the ski lift. I'm going to run right into it. This ski slope is structured really weirdly. It's like a curve. It kind of helix around. As you descend, you end up right back at the bottom of the ski lift. And you want to have just run out of all of your kinetic energy when you get there. Because otherwise, push you through a potential difference. Now you're going too fast. And like we're going to end up somehow getting faster and faster and faster, and the current's going to increase and increase and increase, and we have some kind of like perpetual motion machine, which I don't really expect to happen. However much energy we transfer in through the electrochemistry of the battery, we have to transfer that much energy out so that we're back to square one to be lifted up the electric potential hill by the battery again. Said another way, this sort of thing has to obey conservation of energy. If on the way through, the current is what it is, and the potential difference across the battery is what it is, we know from chapter 18 that there is some amount of power associated with our trip through the battery. Power is energy per time, so it takes some amount of time to do that, and there's some amount of energy. That much energy needs to be accounted for elsewhere. There needs to be a potential difference across this battery. The power transferred out needs to be equal to the power transferred in. E equals I squared R. Now, in order for that to work, now IR is the current through this resistor times its resistance. IR is the potential difference across the resistor. In order for this power and this power to be equal and opposite, this is power in, this is power out. In order for those powers to be equal, the potential difference across the resistor has to be equal to the potential difference across the battery, but opposite inside. Because the current is the current. Whatever current is flowing, we said the current is flowing everywhere in the loop. So this potential difference across the battery, I'm just going to call it delta V battery. In order for this power to add to this power and get us negative, I'm sorry, not negative, to get us 0, P battery plus P resistor needs to equal 0. The current is the same, so we're saying delta V battery plus delta V resistor has to equal 0, which means one of them is the opposite of the other. The total potential difference from one point in the circuit around to it again has to be 0 because energy conservation. All right, what does that mean for us? Suppose we have 3 resistors that we encounter sequentially as we walk through the circuit. We start from the positive terminal, current flows this way, and we encounter this one first, then this one, and then we're back. So let's call them R1, R2, and R3. The potential difference across the battery, I'm just going to call it V. It has a magnitude V. Okay. What do we know? We know that the current only has one place to go. The current must be the same at every point in the loop because conservation of charge. We want this flow, the charge flow rate, to be constant. Otherwise, it's backed up in weird ways, and we don't want to allow that. The other thing we know is that as we walk the loop, the total potential difference that we encounter has to be 0 because energy conservation. So we go through, let's start here. Note that to get from there to there is no potential difference. Those points are at the same electric potential environment because the wire doesn't do anything. It's just a conductor, 0 resistance. To get from here to here, we just went through the battery. We experienced the ski lift. We experienced a positive voltage V. On our way through, we experience the potential difference across R1. Now, to get through R1, we had to spend some energy because there's some resistance there. The energy that we spent, all right, we don't have it anymore. So I'm going to subtract the voltage, the potential difference, the difference in the electric potential environment from one side to the other of R1. How much did our electric potential environment have to change in order to get us through that resistance? Same story, we gotta push through R2. How much did our electric potential environment change in order to get us to do that? And again, same story, to get through R3, our electric potential environment had to change to push us through. All of that needs to add to 0 because now we're back here again. Now, let's move these negative ones to the other side. But the voltage, the potential difference across resistor 1, according to Ohm's law, is IR. Factor out the common current, we end up with this expression. Now, suppose, well, instead of 3 individual resistors, does there exist a single resistor that I could replace them with so that the resulting current is the same? EQ, equivalent, some equivalent resistor that I could replace R1, R2, and R3 with so that the ratio of the potential on the battery and the current stays the same? Yeah. I mean, Ohm's law, right? If that's the potential on a battery, and we want this current, we divide by I. The resulting expression is the equivalent resistance. So if we have resistors in sequence like that, in series, their effective resistance is just their sum. Okay. Now, what if we change the story a little bit? So these are wires, wires, wires. We've got a battery with some achieving some electric potential difference V. We've got 3 resistors again, but now we have them arranged not in sequence. If we are following a path, we turn right and we go through resistor R1, and now we're done. We're back. Because all of these points all the way across that wire, if the wire has no resistance, all of those points are the same. So no matter which resistor we go through, once we're done, we're done. We're ready to be lifted again by the ski lift. We need to have accomplished all of our energy conservation by the time we get through each individual resistor, according to conservation of energy. Now, we go up the ski lift and we get to this this top rail, and we have a choice now. Do we go through R1 or R2 or R3? Because we could do any of them. It's just once we do them, we need to have expended the energy that we have. And that's the trick here. In series, it's the current that is the same all the way around. In a parallel configuration, a branching configuration, right? We get to this point and we can branch off and do R1, R2, or R3. In a branching configuration, the battery is the same. So we get lifted through the battery and we've got a potential difference V that we need to account for. And whichever path we take, we still need to have the same potential difference V, negative, because positive V on the way up and then negative V on the way down so that we're ready again. And that's got to be true no matter what. Now, so that means that the potential across the battery is the same as the potential across R1, as the potential across R2, as the potential across R3. Now, the current flowing through R1, I1, is the voltage divided by the resistance. Write this again. I1 is V, because they all have the same voltage, over R1. I2 is that voltage divided by R2. And I3 is that voltage divided by R3. And there's nothing we can do about that. That's Ohm's law. If each one is experiencing the same size potential difference V, then we divide each by its resistance and we end up with the current through it. I have no choice. Okay, but if a current 1 and a current 2 and a current 3 are all reaching this bottom rail, that's because we're moving charge. And we're moving charge, and we're moving charge. And in order to make sure that as much total charge as we move through the total of the 3 resistors, it's like 3 different lanes, to make sure that we are able to move that same amount of charge, because I don't want any to bunch up. As they come in, I gotta move that much out. The current going through the battery needs to be enough to account for all 3 currents. If we're going to move some charge through R1, we needed to get it from someplace. If we're going to move charge throughout to R3, we had to get that charge from somewhere. And it's the battery that needed to put that much charge all together on the top rail so that we had enough to move through the 3 resistors. In other words, In series, the potential differences had to add. In parallel, the currents need to add. However much current comes into this bottom rail, it's the total that needs to flow out. This current, though, is the current that goes through the battery. The current that goes through the battery. Right. We'll think about that. Now, I1, I2, and I3, we've got rules for those. V over R1, V over R2, V over R3. Let's factor out V. Over R1, 1 over R2. Is there an effective resistance that we could replace this configuration with? In other words, instead of this nonsense, just do that. Yeah. This is the current through the battery. This is the potential across the battery. And if we imagine this, the potential across the battery needs to be the potential across that equivalent resistance. So V, which in this case is the current divided by this whole noise, 1 over R1 plus 1 over R2 plus 1 over R3 needs to be equal to IR. Right? Because that much current, that much total current divided by, or times the resistance is the potential difference. IR EQ. And if we use this equal sign and cancel the common I, we end up saying that R equivalent is 1 over R1, 1 over R2, 1 over R3. The equivalent resistance of resistors in parallel is the reciprocal of the sum of the individual reciprocals. Suppose each of them were the same. Is this any kind of sensible? Each resistor, R1, R2, and R3 are the same. Let's just call them R. If we used one of them, V, R, we would get I. Some current I. What if we use 3 in parallel? Well, according to this, 1 over R plus 1 over R plus 1 over R. So that's 3 over R. But the reciprocal of 3 over R is R divided by 3. Putting 3 of them in parallel reduces the effective resistance by a factor of 3, which would increase the effective current by a factor of 3, according to Ohm's law. I guess that makes sense. If there are 3 resistors in parallel, then I have 3 times as many choices for which path to take. And if we think about them like, if we think about them like pipes that we're trying to get electrons to flow through, having 3 pipes with equal resistance instead of only 1 means that I can move more electrons in any given amount of time. So with the same pressure difference, I can move more fluid. With the same electric potential difference, I can move more charge. I can increase the current, which is what we said. So this is, yeah. That works. If batteries, I'm going to switch gears a little bit. If batteries supply potential difference, and that's what they do, then what does it mean when they die? If I put a battery in my flashlight and I use my flashlight forever, eventually the light goes dim and it won't light anymore. What happened? A battery, you know, your run-of-the-mill battery, it runs on a redox chemical reaction. And that chemical reaction takes place in some electrolytic solution, usually. What happens is that over time, the electrolytic solution dries out a little bit, becomes a little bit less elastic. It doesn't permit the reaction quite as good as it used to. And we can sort of make a model for that by talking about a real battery. Let me draw that this way. A real battery as a source of electric potential difference. And the thing is, the chemical reaction that's taking place has an energy associated with it. Like whatever, however good the battery becomes, or however bad it becomes, it's still doing that chemical reaction. So the energy associated with it is the same, right? The chemical potential energy that we could convert into electrical is what it is. The reaction is the same. It's just a matter of how well the electrolyte permits the chemistry, the reaction to occur. And we can model that with this internal resistance. As the battery dies, the electrolyte dries out, and more and more and more of the chemical energy that's converted into electrical energy, the more of that energy gets spent before we even get a chance to spend it by pushing through that. It's like a ski lift, but it's all rusty, right? So it doesn't lift as well. It's the same hill, but like all the energy that we were putting into running the motor just it can't do as much current in a certain sense. Here's an example. Suppose we have a battery with baseline potential difference 12 volts. And we're trying to do a job with a 65 ohm resistor. let's let the internal resistance of the battery, for now, let's let it be a new battery, low resistance, 0.1 ohms. Now that we've talked about how resistors in series behave, we know the story. We know how much current we get. Current equals V over R. We've got 12 volts altogether, and we're pushing it through 65.1 total ohms because these are in series, so we add them, and we end up with a number 12 divided by 65.1, 0.184 amps. Okay. If we connect our voltmeter from one side of the battery to the other. Now remember, this resistor is kind of internal to the battery. We can still use it in the circuit, but as far as we're concerned with measuring the battery, it's part of the deal. Now, the potential difference from here to here, let's call this point A and point B. The potential difference from A to B is the voltage from the batteries, 12 volts, minus the voltage across the internal resistor R, which is the current (0.184 amps) times the internal resistance, 0.1 ohms. Now, this is going to be very small. 12 minus is 11.98 volts. When the battery is new and the internal resistance is low, things are really close. We end up with an effective 12 volts like we expect. I mean, pretty close, right? As time goes on, battery gets a little more tired. What if at some point later the internal resistance is 1 ohm? So it's 10 times worse than it was. Right, well, let's find out. The effective current we're going to get now is as a result of needing to push through 66 ohms. So we're going to get a little bit less current than we did. 12 divided by 66 is 0.182 if we round. All right, so not that much different. But if we use this number here, 12 minus that answer times not 0.1, but 1, (11.8). So we've reduced our effective voltage, the effective from terminal to terminal voltage of the battery by, well, not a lot, but it could be significant. How much power are we dissipating? Well, at a certain point, we might have so large an internal resistance that the power supplied by the battery is not enough to do whatever job it is that's associated with 65 ohms. Maybe this is power a flashlight, and there's some amount of energy that is released into the brightness of the flashlight beam. Whatever the wattage rating of that flashlight is, if we have so much internal resistance that we don't have that much power, the light bulb's not going to light, or it's going to be dim at any rate. So the textbook presents a formula for us, a way to sort of contextualize in an equation internal resistance of the battery. At the terminal to terminal voltage, I'm just going to call it V terminal. Potential difference across the two terminals of the battery. This is terrible. The textbook uses it, and even the textbook calls it out as being confusing. This expression is just this expression written in variables. There is like the base rating of the chemistry of the battery, and then we subtract the current and the internal resistance. It's just that written in symbols. What is this? We'll call it the EMF. Where does that come from? It's a terrible name. The EMF stands for electromotive force. The oomph that gets the electro to move through the circuit. I understand why they named it that way. It isn't a force, and this isn't really motion in a really good kinematic sense. It's a terrible name, but it's the name we have. And what it means, EMF, is the potential difference associated with the chemistry that the battery is constructed to use. Whatever, electrolytic reaction is supposed to happen in the battery, there is some energy of reaction associated with that. Divide by, talk about energy per charge. That's this. It's the energy per charge of the reaction that is the chemical part of the battery. Gonna end up having to use this funky symbol. It's like a script letter E for EMF. Horrible name, but I think it makes sense what it's referring to. All right, next segment.